So good morning. For today, we'll be discussing about microprocessor system design. So for the outline, of course, we'll be discussing about simple objectives, digital system design, microprocessors, history, numbering systems, and arithmetic operations. So these are some of the topics that we needed to cover. As per the objectives, basic understanding of the architecture of microprocessor, basic understanding of the operation of the microprocessor, assembly language for control and interfacing applications, although we have separate machine experiments and further discussions about assembly language as we go along. And then introduction to Intel 8086 family up to Pentium 4 and interfacing. So let's now discuss about digital system design. Digital system design finds diverse application across various domains, playing a pivotal role in shaping modern technological landscapes. In signal processing, it facilitates the manipulation and analysis of signals for tasks like audio and image processing. Control systems rely on digital design for precise and efficient regulation of processes, while communications benefit from digital systems for encoding, decoding, and transmitting data. Microcomputers, integral to personal computing, are a direct outcome of digital system design. Robotics harnesses this technology for intricate control and automation. In multimedia, digital systems enable the seamless integration of text, graphics, audio, and video. The Internet heavily relies on digital designs for data transmission and processing. Moreover, digital systems enhance distance learning by providing scalable, interactive, and accessible educational platforms. In essence, digital system design permeates through an array of applications, powering innovations and advancements in our technologically driven world. So let's now discuss about the solutions. Large-scale integration or the LSI chips are densely packed circuits that integrate a large number of components onto a single chip, enhancing efficiency and performance. Printed circuit boards or PCBs and the 70 series are examples of early integrated circuits. Very large-scale integration or BLSI design, including application-specific integrated circuits or ASICs, involves packing even more components onto a chip for specific applications. Standard cells, gate arrays, and field programmable gate arrays or FPGAs offer flexible design options. Embedded microcontrollers, general purpose processors, and special processors are cater different computing needs. So system on chip SoC integrates various components into a single chip for streamlined functionality. So the trio of hardware, firmware, and software collaborate to make these technologies functional, with hardware encompassing the physical components, firmware serving as intermediary code, and software providing user interfaces and applications. So microprocessor base are more reliable, less expensive, easier to debug, easier to maintain, easier to upgrade. However, the disadvantage is relative to speed. So let's now discuss about the design process. The design process in computing encompasses three key stages: system design, interface design, and the program design. System design involves defining the overall architecture and structure of the entire system, outlining its components and their interactions. Interface design focuses on creating user-friendly interactions, designing the layout and functionality of interfaces to ensure a seamless user experience. Program design drills down to the specifics of individual software components, detailing algorithms and data structures to execute the desired functionalities. Together, these stages ensure a holistic approach to creating effective and efficient computing solutions from the overall system structure to the user interface and the underlying program logic. So, this comprehensive design process is crucial in developing a successful and well integrated software systems. The design process involves a structured sequence of steps to create effective solutions. It begins with defining requirements, identifying the needs and constraints of the project. The development of specifications follows, outlining the detailed functionalities and features. Preliminary design establishes the initial system architecture, while intermediate design defines the components and interactions. Detailed design delves into specific elements, specifying algorithms and data structures. Implementation translates designs into executable code. The process concludes with verification and acceptance, ensuring the system meets the defined requirements and specifications. This systematic approach ensures a well thought out and thoroughly validated solution, contributing to the success of the overall project. The typical computer hardware block diagram revolves around the central processing unit or the CPU or microprocessor, which serves as the brain of the system. The microprocessor interacts with various components, including all the memory hierarchy, RAM for temporary data storage, and storage devices for long-term data retention, input and output or I/O devices for communication with the external environment, and the system bus that facilitates data transfer between different components. Additionally, supporting subsystems such as the chipset, which manages data flow between the CPU and peripherals and the motherboard, providing the physical platform for hardware integration, play crucial roles. This interconnected system ensures the coordination and execution of instructions, enabling the computer to perform a wide array of tasks. In the evolution of computing hardware, the 1940s marked the era of vacuum tubes, which were large and power hungry. The introduction of transistors in the 1950s brought about a significant reduction in size and power consumption. The first integrated circuit or IC emerged in 1959, paving the way for more compact and efficient designs. Intel's 4004 in 1971, with its 4-bit architecture and 2,300 transistors, represented a milestone in microprocessor development. The 1970s witnessed the rise of processors like 8080, 8085, say 80, 6800, and 6500, powering both appliances and computers. The 1980s saw the advent of reduced instruction set computing or the RISC architectures, emphasizing streamlined instruction sets. This chronological progression illustrates the transformative journey from bulky vacuum tubes to the more efficient and powerful microprocessors of the modern computing era. Numbering and coding systems are essential in the realm of microprocessors, as they provide a standardized method for representing and manipulating information within these digital processors. Binary code based on the binary numbering system 0 and 1 is fundamental to microprocessor operations. It allows the representation of data, instructions, and memory addresses in a format that the microprocessor can interpret and process. Hexadecimal notation, a base 16 numbering system, is often used for human-friendly representation of binary coded values in programming and debugging. Efficient coding systems enable concise expression of complex instructions and data, optimizing memory usage and processing speed. Without these standardized numbering and coding systems, the intricate tasks executed by microprocessors, from arithmetic calculations to logical operations, would lack the systematic organization necessary for effective computation and communication in the digital world. Numbering and coding systems are crucial in computing, and Unicode stands out as a standard used to consistently encode and handle text in various writing systems. One particular encoding format within Unicode is UTF-8, which is a variable with encoding capable of representing every character in the Unicode character set. It was designed with the aim of being backward compatible with ASCII and avoid complications related to ingest and byte order marks in other encoding formats like UTF-16 and UTF-32. Notably, UTF-8 has become the primary character encoding for the World Wide Web, being employed in over half of all web pages. As for the summary, we talk about digital system design, under which microprocessor base, hardware, software, and firmware. We also talk about types of microprocessors, history, numbering systems, and arithmetic operations. Thank you very much.